저거 치우면 치워질걸요?
차라리 리포 갔다 올까요?
다른 이쪽 스크린으로 못 넘어오나? 네네.
여기 좀 갔다 올까요?
그럼 될거 이쪽으로 갖다 놓으면 될
Okay, we are ready when you guys are.
All right, let's get started. Let me introduce our prestigious speaker, Professor Hae-Won Park from KAIST. Today, he will give us a talk with the title of the hardware design and control algorithms for agile and versatile leg robots. As title suggested, Hae-Won has made numerous impactful work in leg robot by inspired robotics, control algorithms, learning, and so on. And he's also a recipient of the NSF Career Award, as well as the RSS Early Career Award. So please welcome our today's speaker, Hae-Won, and Hae-Won is all yours.
Hello, can you hear me? Right?
Yes, we hear you.
Okay, so thank you for nice introduction, and then thank you for inviting me here to give to have a chance to talk with talk at Georgia Tech. So it's actually my third time to visit Atlanta. I visited here for during my postdoc, and then today weather is actually very unusual to me. I mean, I think it's also unusual to you. But yeah, I actually a little bit sad that I missed chance to give a seminar in person. But anyway, so let me start. So today my topic is hardware design and control algorithm for agile and versatile legged robots. So I'm basically a legged robot researcher. So I do control design and then hardware design for legged robot. So still great examples of the legged robot system is actually biological animal, especially the as you can see in this video, humans have extreme balance capability to climb the to climb the wall, rock climbing, without utilizing his hand. And then this dynamic balance can be achieved by this funny looking, very fast leg kicking performed by Ukrainian dance performer. So this agile and then very dynamic capability provided a great balance and then very agile performance in biological animal system, including human and then some quadrupedal animals. But this video shows another level of athletic mobility, and then this is a squirrel. We assume that this animal does not have a very intelligent capability, but this animal can quickly jump over gaps and then obstacles, and then while utilizing its full body capability and then physical limitation, something like that. So you can climb the rope and then utilizing as you can see here, some ladders. And then even you can ride on some elevator mechanisms to navigate through very complex environment. So here we can see that very intelligent behavior. It can combine many locomotion skills to come up with the navigation on very complex terrains. So in our lab, we are trying to reproduce the kind of capability in legged robot system. So of course we do hardware design and then hardware implementation, and then so we manufacture our own hardware. And then we implement our control design in our robot. So this video shows our robot Hound actually navigate through climb up the hilly mountain nearby the KAIST campus. So in this talk, I will show two robots. The first robot is KAIST Hound, and then this robot is designed for fast running. And then to do that, we designed our own custom motors, and then we installed that motor to our robot. And then second robot, I will try to show is a marble robot. And then this robot is designed to climb the vertical surface very quickly. And then this robot equipped with the novel magnetic foot, which can provide the radiation force. And then to implement that, we utilize the electropermanent magnet. And then unlike the electric magnet, this magnetic device does not need electric energy to keep the magnetic force on. So we only need magnetic energy. We only need electric energy when switching between on and off state. Okay, so you can save some energy by utilizing this electropermanent magnet. And this switching can be done very fast, in a very fast manner. And then for this novel hardware, we design our own control algorithm. So we utilize two frameworks, two approaches. The first one is a model-based control algorithm. Specifically, we utilize model predictive control. And then we do some study on the model itself and then algorithm, optimization algorithm itself. And second approach is actually learning-based algorithm. So we employ the reinforcement learning algorithm, as well as we are now studying about some hybrid type algorithm which can combine product optimization and reinforcement learning algorithm, which is an ongoing study now. So to design the control algorithm, we have to come up with a control algorithm which can respect hardware characteristics as well as limitations. Okay, and then some hardware like magnetic foot has some unique function which did not exist. Okay, the previous hardwares. So we need to come up with a simulation algorithm in order to reflect this new hardware and then hardware characteristics and limitation. So in this way, we can actually fully utilize the hardware capability of existing system. Okay, so sometimes we have a hardware specific simulation model. So we add this kind of simulation model to existing software for dynamic simulation. So for example, actuator dynamics can be implemented. Okay, so actuator is not just a pure torque source. It has its own dynamics. So electric motor has its own dynamics. So we add that in the simulation model, as well as a novel hardware model. So we mathematically model novel hardware and then add it in the simulator. Okay, so to come up with this particular climbing in the simulation model. Okay, and then the design control algorithm requires model-aware control design. So in the design of control algorithm, we have to consider or we have to respect this hardware-specific simulation model. For example, reward function has to be carefully designed so that it can reflect this hardware specifics as well as a constraint in your reinforcement learning algorithm or model-based control. Okay, model-based control design. So today I will talk about how to implement this or how to come up with and design the hardware-specific simulation model and then model-aware control design. Okay, and then of course, as a experimental roboticist, we encounter a lot of moments of catastrophic failure, and then we can learn something from this experience. So for example, this is my Mabel robot for my PhD. And then we broke Mabel's foot, Mabel's ankle. But don't worry, it takes about only like 30 minutes to fix this leg. And then for MT-2 robot, for my postdoc, has some amplifier explosion. And then some weird behavior that was not designed by me. And then this KAIST robot fell because of the bad control. So this failure provides us some lesson, but especially these two failures actually motivated us to design new control algorithms. So we will get back to these two failures later, okay? So first of all, let's talk about the hardware design. So we are utilizing quasi-direct drive, or so-called proprioceptive actuator, which was originally proposed by Professor Sangbet's group, okay, at MIT. And then we kind of agree that this QDD actuator was actually enabler, okay, technological enabler for the success of quadruped robot, as well as some humanoid robot, okay. The idea is actually very simple. We utilize high torque motor as well as low gear ratio gear reduction mechanism in order to improve the transmission transference, okay, and then improve the backdrivability, okay. So here I'm showing you the proprioceptive actuator design with the low gear reduction ratio. But how much gear reduction ratio we have to utilize? So in order to answer this question, we utilize trajectory optimization algorithm. So in the previous method, the design procedure is actually very iterative and sequential. So here we select gear ratio, and then the selected gear ratio determine the operating region of the motor with respect to torque and then omega, angular velocity. With this motor operating region, you solve constraint trajectory optimization algorithm and then obtain the trajectory. And then we check that this obtained trajectory satisfy your desired performance. And then if it doesn't satisfy the design performance, then we go back and then iteratively select the new gear ratio and then do this again, okay? So in our work, we combine all of this process in one nonlinear optimization problem, and then we come up with a new nonlinear optimization problem. Here, we try to maximize jumping height while reducing the impact force upon landing, and then respecting limitation on actuator torque and speed. Okay. And then we formulated the nonlinear programming problem with this performance specification. And then when running nonlinear programming algorithm, we obtained the gear ratio of 22.9 to 1, which is actually a little bit higher than MIT Cheetah case, which was 5.8 to 1. Okay. And then to realize this gear ratio, we have to design compound planetary gear mechanism. And then this is the performance of the jumping height over the leg installed with the actuator we designed. And then this leg is actually implemented in the marble design. Okay. Next design optimization we did is actually, now we try to include the number of gear teeth in our optimization problem. And then number of gear teeth is an integer variable. So now the problem will become nonlinear, mixed integer nonlinear programming problem, right? So you have a number of gear teeth of the ring gear, sun gear, and planet gear. This combination will provide the gear ratio, and then this gear ratio will affect the many things like motor selection, swing rate, trajectory, energy cost, something like that. The benefit of having this number of gear teeth in your optimization algorithm is actually you can consider the hardware specific design or detailed design. So for example, number of gear teeth of the knee gear should be larger than or equal to some value to avoid the undercut, okay? And number of gear teeth of hip sun gear should be larger than or equal to this number in order to make the shaft go through the hole which is in the hip gear, right? For example. So this kind of specific design consideration, okay, can be included in optimization problem if you consider number of gear teeth, okay? And then finally, planetary gear assembly constraint, so that you can assemble this number of gear teeth, the gears with the number of gear teeth, okay, to make the planetary gear set, okay? And then if you solve this optimization algorithm, you can obtain the gear ratio as well as the number of gear teeth. And then this number of gear teeth can be directly used to design the planetary gear set, okay? So we designed our planetary gear set and then motor module, and then we installed that in the KAIST Hound robot, okay? So this is how we design the quasi-directed drive actuator to select the gear ratio, okay? We utilize a planetary gear set. Since I don't have much time, I will just directly go to the control design. The first control method is a model-based control design, specifically model predictive control. So in model predictive control, we try to solve this very small optimization problem. And then it has real function, state transition model. And then if you solve this finite time optimization problem, then you can obtain the set of sequences of actions. And then you implement this sequence only the first input, first action, okay, at t equals 0. And after that, at the next sample time, you solve again this optimization problem, okay, and then obtain the sequence of actions, and then only apply the first control actions, and then go so on and so on, okay? Then you can obtain feedback, okay? And then this optimization problem should be solved within around 10 milliseconds in order to make real time, okay? But the problem is the transition model is actually very complex because the robot consists of multiple rigid body, okay? It's actually high degree of freedom model. So what we do is actually reduce model complexity. So we took out the contact dynamics model, and then we assume that the robot is actually just one rigid body, and then this rigid body is controlled by ground direction force, okay? So with that, we can actually can read over contact dynamics, okay? So because we don't have contact dynamics, the contact sequence should be predefined, okay? It cannot come from the optimization algorithm because optimization algorithm doesn't know the contact dynamics, does not have a contact dynamics. So we normally predefine the sequence of foot, for example, trotting gait, bounding gait, and then galloping gait. And then we design the MPC algorithm, okay? And then this method is already has been utilized to come up with autonomous jumping over MIT Cheetah 2. Okay. So if you look at the robot as a single rigid body dynamics, then those two robots actually have the same mathematical structure, okay? So KAIST Hound and then Marble robot, they have the exactly same model, but different inertial parameters, okay? And then different foot contact constraint. Hound robot has to satisfy Coulomb friction constraint. The Marble robot has to satisfy foot contact constraint imposed by magnetic foot, okay? So it's a little bit different, so. But they share the same dynamics, and then they can use the same optimization algorithm, okay? So here in single rigid body dynamics, if you are working on the 3D single rigid body dynamics, you have this manifold variable R, which lives on SO3 manifold. And then normal like MPC algorithm convert that into Euler angles, okay? And then Euler angle has some problem, some issues, mathematical issues. So it does not provide a consistent distance between two orientations. And then it suffers from the Kimbalak problem. So it suffers from the singularity. Okay. So to get over this problem, in just a normal robot, it will not be problem because it walk on the flat ground. It does not go like vertical surface for just normal robot, but for marble robot, it has to climb the vertical wall. Then it will go through the vertical posture, which is actually singularity for oil angles, right? And this experiment actually failed because of the problem. Okay, so there are many types of Euler angles, and then some Euler angles has the singularity when your angle becomes 90 degrees. So I picked up wrong Euler angle choice, so that resulted in this failure. Okay. So now we formulate a model MPC problem in on SO3 manifold. Okay. Then the optimization problem becomes optimization on SO3 manifold. Okay. And then we utilize a reparameterization trick in order to make this optimization on problem to optimization on vector space problem. Okay. And to solve this problem efficiently, we need Jacobian, analytical gradient, and Hessian. Okay. So we specifically use Gauss-Newton Hessian algorithm. Okay. And then we actually adopted the method presented in this paper, published in TRO in 2016. Now, after this, it becomes quadratic programming problem. And then we utilize our own custom QP solver. Okay. And this is the result of running fast with 3 meters per second. And the robot can handle very wild kicking. And then now we can transfer this control algorithm to climbing robot as well. The only thing we changed is actually foot contact constraint. So we derived the new contact constraint for magnetic foot so that it doesn't slide or peel off. Okay. Then new contact constraint is actually intersection of these two constraints. Okay. And then when implemented our algorithm to the robot, we can obtain the pace gate with the speed of 0.7 meters per second, as well as inverted throttling gate with the speed of 0.5 meters per second. And then the magnetic foot, and then robot is powerful enough to handle 2 kilogram payload for vertical climbing and 3 kilogram payload for inverted throttle walking. Okay. And then if you utilize some trajectory optimization algorithm, then you can come up with this trajectory which can traverse the gap. Okay. And then making transition from vertical wall to inverted wall. And the robot was also tested on the outdoor experiment. This is actually water tank made of steel, but it's actually covered with very thick paint. So paint depth, thickness is actually 0.3 millimeters. But the magnetic force is strong enough to provide the radiation force still. And this method can be also applied to state estimation, because the state estimation is basically another optimizer problem, right? And then we proposed the invariant smoother for state estimation for our robot, and then it provided the best result compared to state of algorithm. Okay. Okay, now let's go back to the second failure. So this is the second failure. what happened to robot is actually stepped onto the non-moving part of the treadmill. And then even with this very corner cases, the robot does not change the gait to recover from the corner cases because it does not have that ability because we predefined the contact sequence in MPC design, right? So now we want to include the contact model in our model MPC problem. So here now we add contact impulse to our transition model. And then this contact impulse is obtained by solving this optimization problem. Okay, this optimization problem has a cost, quadratic cost, but it has some constraint. Okay, and then this we call complementarity constraint. And because of this special structure of complementarity constraint, the solution of the problem will be categorized into 3 cases. Okay, the first case is a separating case. So after the impact, the robot's foot leave the ground. Okay, this is easy. And then clamping case. Okay, so after the impact, robot's foot stuck with the ground and doesn't move. Okay, in this case, after the impact, velocity becomes 0. And third case is a sliding case. Okay, third case, the robot slide. Okay, after the impact. So for each cases, we can obtain the analytical solution of impact contact impulse. And then because we have an analytical expression, we can obtain analytical gradient, okay, with respect to some physical quantity. Okay. So for clamping case, we can see that after the impulse, the velocity becomes 0. The foot velocity becomes 0. So any gradient of contact velocity with respect to some variable will become 0, right? And this results in local minima, actually. So for example, let's say you are, in this robot, the reference position is actually very up. Okay, the robot has to jump in order to match the reference position, right? But it does not jump because it is in clamping mode. It starts with the clamping mode, then gradient dies. Okay. The desired solution is something like this: periodic jump to match to the reference position. Okay. So if you see the gradient, then you can see that there is a local minima on the left half side of space. To solve this problem, so the solution of a complementary constraint, the space of that looks like this. Okay, it can be either vertical line or horizontal line. Okay, we actually approximate that space with more smooth and continuous space. Okay, something like this. And then we introduce that this is a more continuous and smooth space by introducing the variable rho, which is a positive value. If rho is very large, then it actually does not approximate well with the original constraint. But if rho is very small, then it approximates very well the original constraint. So we have actually adjusting knob. Okay, how well we approximate the original constraint. So original analytical gradient, the robot tends not to jump. And there is actually a previous method with some heuristics. This does not provide the periodic, okay, jumping behavior. So if we use our method, then it provides very periodic jumping, and then it can reduce the cost a lot. Okay. And then if you look at this this gradient, you can see that when rho equals 0, this is actually the same as the original constraint. There is still local minima on the left. As we increase the rho value, it actually converges to global minima, even though it starts with close to the local minima point. But if you increase too much, then the solution, the quality of the solution is actually become worse. Okay. So there should be some sweet spot over the values of low. If value is too small, it does not jump. If value is too large, then it jumps too often, which result in bad cost value. There's actually pretty wide sweet spot that provide pretty good reward value, okay, cost value. Now we integrated this analytical gradient with differential dynamic programming. In forward pass, we have an exact impulse model. In backward pass, where we need a gradient, we use approximated smoothed analytical gradient. And then we employ the multiple shifting variant of DDP to improve the convergence property. Okay. So if you implement this algorithm to real robot, to the simulation model, so on the top, you have a reference trajectory. There is no swing trajectory. There is no foot contact sequence, but the algorithm automatically come up with a new contact sequence. Here, slippery surface. The robot sometimes utilize the slippery surface. Sometimes it propel the, okay, so that it can catch up with the reference if required. And then this cartwheel motion. The algorithm can come up with this nice cartwheel motion. Okay. And then if we extend this idea into the 3D model, we add some additional reward that can prefer floating gate, symmetry gate. Okay, that's the only the added reward functions. And then you come up with this nice motion. And then for this unstable posture, this is actually very unstable posture. The robot come up with this nice motions to catch up with this unstable posture. Okay, so there is no equilibrium in this unstable posture. Okay, the only way to follow this reference is actually making contact. Okay, and then you can obtain the humanoid robot motion by just changing the reference. Okay. Now the robot only utilize its hind foot. Okay. We implemented this algorithm to real robot. So of course we did a tremendous of the amount of engineering to make this algorithm in real robot, which cannot be contained in the journal publication, sadly. But anyway, so the computation time satisfy the real-time constraint. And this unstable pose can be followed. Okay, there is no equilibrium. There is no dynamic equilibrium. So that's why the robot cannot keep this posture, but it tries as much as possible to follow the reference trajectory, reference posture. Okay. So second approach we are currently utilizing is actually reinforcement learning, and then we recently published the robotics and automation magazine paper. So my student really wanted to work on the reinforcement learning, and then this is his first controller. So this controller can come up with this 4 meters per second fast running. So 4 meters per second is already better than model-based control, right? Model-based control speed was maximum speed was 3 meters per second. And it actually was able to handle the corner cases, even though it stepped onto the non-moving part of the treadmill. It can recover from these corner cases. But if you look at a gate, it looks strange to me. It looks not natural to me, right? I mean, animal utilize this kind of gate. You can see. I'm not sure why they are utilizing this gate. It doesn't look energy efficient to me and natural to me. But they say they exhibit this gate when the animal is happy, right? So, but we don't have a happiness beyond function, in our design. So to evenly distribute the torque to the symmetric foot, we add the trotting gate preference in the other function, and then we can come up with a more natural gate, which provide the faster speed. So the speed was increased to 5.16 meter per sec. Okay, we have 1.16 meter per sec speed increase. To further increase the speed, we actually employ the motor operating constraint. So in the URDF file, you can actually specify angular velocity constraint and then motor torque constraint. They are actually separate. So they will provide a box constraint. But real operating region of motor space is not actually box constraint. It looks like that, okay? Because of back EMF and resistance. If you have inductance in your model, then it becomes ellipsoid, okay? But we only consider resistance in our model, and then we obtained this motor space, motor operating region. So if you see this, okay, torque and angular curve, you see that it does not utilize much of the region, okay? So we implement the motor operating region in our reinforcement learning, and we gained actually higher speed. We obtained 0.5 meter per sec increase, okay, speed gain, okay? By just adding that constraint, okay? And then you see that it more fully utilizes the motor operating region, okay? And then as a mechanical engineer, we have a choice of changing our mechanical hardware. So we change the foot so that it becomes more like it becomes less heavy. And then we obtained the 6.5 meter per sec running. And this is actually 2 years back. So we broke this record, and then some other institution broke our record as well recently. And then the robot finishes 100 meter per sec dash within 9.87 seconds. And then this made our robot to have a Guinness World Record. I mean, yeah. And then reinforcement learning algorithm can come up with the galloping. So if you have a dog or cat in your home, you know that they don't utilize trotting gait for fast motion, right? So we can actually implement the galloping motion, but sadly it does not provide a faster performance. We don't know why, but. And then as I showed you already, we utilize a reinforcement algorithm for this robust walking on the mountain. Okay, let's skip. So we are trying to implement this reinforcement learning algorithm for climbing robot as well. If you have a non-magnetic surface, then if you use MPC algorithm, it actually fails, okay, as you can see, because it cannot attach to the non-magnetic surface. But in the gecko case, you can see that even though it fails to attach its foot, it can recover from it, right? If you use RL, even though it failed to attach to the surface, it can actually recover from it, okay? And then if you integrate this RL algorithm with the vision feedback, we can obtain this very dynamic and agile performance. So this is about 4.0 meter per second running. Okay. And also do outdoor experiment. Okay. And then recently many humanoid robot has been shown by many companies and in industries. We don't have a humanoid robot yet, but we can show that just utilizing the actuator technology and then reinforcement learning algorithm that we have now, we can probably come up with a humanoid robot control algorithm. So even though we don't have a humanoid robot, we can make the quadruped robot work like humanoid by without changing any hardware design. So we didn't change any hardware design, but it can actually run up to 3.5 meter per second now. And then it can recover from kicking from the experimenter. Okay. And the nice thing about this control design is actually it does not have enough degree of freedom for side kicking because we don't have an actuator for that. But it can actually recover from this kicking as well. Okay. And then we can also make the robot to lift some payload, which is about 7.5 kilograms. Okay. And then now we are actually trying to improve the record of the quadrupedal robot running. Now the fastest speed we could obtain is actually 9.5 meter per second. And then the robot can finish the 100 meter sprint in 11.6 seconds, which is probably faster than most of you audiences here, including me, right? And then we are also trying to break the record of the human by Usain Bolt. But as you know, we have a lot of failure moment, and then we are hoping that we can learn from something from this as well, the failure moment as well. Okay. So with that, I want to conclude my talks, and then I want to express my I'm grateful about my collaborator as well, including Hae-Won at Georgia Tech. Yeah, and then thank you for your attention. Yeah.
I think we have time for a couple of questions, maybe via Zoom or the maybe some in-person audience. We have a handful of audience here. So any questions? Yep. Oh, wait. Let's start from the in-person question, and then we will go back to Zoom. Right. You can ask a question.
Okay.
Can
So
you repeat
the-
the question just
the-
in case?
Question is about have you implemented any machine learning algorithm to come up with the combinate the design problem combination design problem of hardware design and control design, right? Okay. Not yet. I mean, we have not done yet. Okay. So and then the difficult thing about the hardware design work is actually, let's say we come up with some value, and then we have to actually manufacture and then assemble the real hardware to prove its efficiency or its efficacy. Okay, so actually we cannot have like many cases to prove this method works. So it's actually very difficult. And then I mean, the optimization algorithm is not perfect. Sometimes it provides weird answer. So I have not actually extended this work yet. Okay, yeah.
Right. I think there was a Zoom question. So yeah. Maybe we can start from the top.
Yes. Okay. So the first question is actually a very practical issue. In order to be certified by Guinness World Record, you need resource and time and then effort. They are not very responsive. Okay. And then you need some money actually, like publishing paper. So if you are planning to break the Guinness World Record, you guys can contact me. We actually consulted have a consultation with the Jonathan Hurst group from Oregon State University because they broke the world record of humanoid walk running, right? So we actually took advice from them, and then we successfully contacted the Guinness World Record. So it's actually a practical problem. And then even though you break the record once again, I don't think it's not related with the publishing another academic journal papers, right? So that's the reason.
Right. Next is, I think, Frank. Is it? I think so. Yeah.
Yeah.
Frank.
Hey, hope you can hear me.
Yes.
Awesome talk. Really awesome talk. My question is, you switched from MPC to reinforcement learning. And so I wonder whether you were able to learn something from reinforcement learning that we can use in MPC world. So what is your lesson from switching to RL?
Yeah. So I mean, theoretically, I'm not sure what I can learn from this reinforcement learning algorithm, but for practical reason, I think in the world of MPC, model-based algorithm, I think we need some well-packaged open source, I think, suite of code, I think, to make them like more widely used. Okay. So in the area of reinforcement learning, they have a really good package, really good open source, code base you can download and then implement. I think that can actually spread the algorithm to more wider audiences or more wider engineers. I think we need that for a model-based control society more. And then RL algorithm, I think is really good at come up with some emergent behavior that was not expected by humans. So actually, when the robot collide with the stairs, it actually changes the swing gait automatically so that it actually picks up the leg higher than usual and then to step onto the next stairs. Okay, so this algorithm, this kind of behavior was only enabled by like additional design of swing trajectory algorithm, swing trajectories, right? But in RL, you don't need to have an explicit algorithm for this. It's actually embedded in your neural network, like weight functions. So this was not expected by me. Yeah, I hope this answers your question.
Yeah, that's awesome. Thank you.
Right. Let's do one more Zoom question and we will get back to you.
Okay. One mechanism is keeping the quadruped attached to vertical and inverted surfaces. So you are asking about the marble robot, right? So we use a magnetic foot. We use a magnet, okay? And then the surface is actually consists of steel. So the robot only is able to work on magnetic surface, steel surface, okay? So, I mean, people like, they have actually complaints when they see our video, like, why don't your robot work on like more variety of surface, like concrete surface, something like that. But we believe that there's actually many industrial application this magnetic worker, because in many industry environment, for example, shipbuilding industry, okay, the ship is actually made of steel, but they don't have any. They actually still utilize the scaffold to, you know, people work on the ship surfaces. It's actually very dangerous and then very costly. Okay, so we are hoping that this kind of robot can be used in the shipbuilding industry, or like factory inspection consisting of a very large storage tank, something like that. So yeah.
Right, let's go back to one in-person question and we will get back to the another online question. Can you ask us question?
Are you experimenting with the length of the arms and legs to increase gallop?
That's true. That's actually very difficult to answer. I mean, I'm not sure there exists any optimal length of the leg to provide the optimal behavior. It's a difficult question because the design parameter for length of the leg is actually multiplied to the control torque. Okay, so it's actually very complex kind of bilinear mathematical problem. So I don't think there's actually true optimal for this problem. So yeah, we have not. Thank you.
I think we have a
Thank
couple more
you for the talk. Can you please reiterate how you overcome your problem of gimbal lock? Thanks. Okay, so the previous obtained problem, they reformulate utilizing the oil angles. We don't utilize oil angles. We formulate all the cost function and then constraint only utilizing rotation matrix. Okay. And then this rotation matrix representation can be converted to the vector space representation utilizing reparameterization. Okay. So that becomes that can make the problem become vector space optimization. Now you can utilize a traditional optimization solver to solve this problem. Okay, so yeah, that's how we avoid the Zimbala problem. The next question is, when the robot is at its max speed, is there any control policy that enable it to stop safely and rapidly without breaking the hardware? Okay, so I think currently the robot can accelerate and decelerate in a pretty quick manner. Okay, we have not measured the maximum acceleration, maximum deceleration that provide a stable transition, but now it's pretty good. It just satisfy our needs. But I think another way to provide the better deceleration, acceleration would be designing another like transition control policy, which provide better, okay, transition, like quick transition. But yeah.
Oh, actually, we need to move soon. So I would like to actually, sorry, I believe you have many questions, but I believe the Agile's question will be the last one, I think. Yeah.
Any thought on RL augmented MPC?
Yeah. Hey, Hae-Won, this
Yeah.
is a very nice talk. So
Okay.
Yeah,
Thank you.
I think I'm just curious. Things you mentioned, the RL, the MPC, model-based approach is really good at giving very reliable motions, but maybe less, versatile or emergent as what RL can do. And I'm just curious if you have any thoughts, combining them, or maybe for certain type of tasks you just use RL, for certain type of tasks you just use MPC. Or you think maybe combined RL with MPC can solve, a lot of different kind of tasks.
Okay, yeah, thank you for your question. So, I mean, we have some preliminary work, collaborated with the Seunsu group, as you know, like we have a imitation learning of MPC, and then we train further that policy with the reinforcement learning, and then we are still working on that direction. And then another direction we are taking is actually it's kind of utilizing autoencoder structure, like foundation model. So if we have lots of trajectory data samples, and then we can learn from autoencoder, okay? And then to imitate it, to actually sample that data samples, and then we can probably add reinforcement learning, like a fine-tuning of the large language model. Probably we can come up with some new controller. Actually, the vision feedback learning that I showed in this talk is actually controlled by the kind of algorithm now. But we have not published any paper yet. Okay, we are working on writing paper.
Okay.
Right. Thank you for all the questions, and also let's thank the speaker again. And yeah, there's one. Yeah. If we have more questions, yeah, sure. Feel free to reach out to me or directly Professor Hae-Won Park. And thanks for all the participation, and see you. All right. Thank you. I think we can quit. Yeah.